My name is Jennifer Lautenschlager, and I'm going to be presenting electricity and how it moves through the body. So what is electricity? Electricity is a form of energy resulting from the existence of charged particles, such as electrons or protons, either statically as an accumulation of charge or dynamically as current. So what are some of the components that go along with it? Some of these components include electric shock, which is defined as the sudden violent response to electric current flow through any part of a person's body. Electrocution is death caused by electric shock. Primary electrical injury is tissue damage produced directly by electrical current or voltage. How is electricity measured? There are many different formulas, and one of them is current. So what is current? Current refers to the amount of electricity, electrons, or ions flowing per second. Current is measured in amperes or milliamperes. Contact current occurs when a person touches conductive surfaces at different potentials and completes a path for current flow through the body. Such currents provide an additional coupling mechanism to that, due to which direct field effect between the human body and low-frequency external fields. Here are some other ways that electricity can be measured and calculated. Current, as I already mentioned on the previous slide, is here. Voltage is the difference in electrical potential between 2 points, which is defined as the work needed per unit of charge to move a test charge between 2 points. Resistance is the opposition that a substance offers to flow of electrical current. It is represented by the uppercase R. The standard unit of resistance is the ohm, sometimes written out as a word and sometimes symbolized by the uppercase Greek letter omega. Power is the amount of energy transferred or converted per unit of time. In the International System of Units, the unit of power is the watt, equal to 1 joule per second. In older works, power is sometimes called activity. Power is a scalar quantity. Many unique characteristics have been investigated in various studies in human-computer interaction and related research fields. Such studies include applications for using the body as a conductive lead for transmission or electrical field sensing and activating human muscles or organs. One of these unique effects of electrical impulses that the body sends off is from the heart. The rhythm of our heartbeat is controlled by electrical impulses. It is because of these impulses we're able to actually record and physically document what they look like by using an electrocardiogram. Also known as an EKG, an electrical cardiogram can help predict many things based on the electrical impulses of the heart. For example, an EKG can help detect an irregular heartbeat called an arrhythmia, and even detect if someone is having a heart attack. If you take a look to the right at the top, I have a picture of what an EKG machine looks like. Usually, this is something that your PCP will do to you just to make sure your heart is okay and that your heart rhythm is okay if you're over the age of 50. Down below, I actually have a picture of what the printout of an EKG would look like. If you look at the top hand right corner, you can see that the rhythms look a little bit square. That shows that a person is having a STEMI or a heart attack. And this is very helpful in getting immediate treatment, especially if this is found in an emergency situation. Despite the heart having its own electrical capabilities, electricity is not completely safe for the human body. Human skin and hair easily lose electrons and cause static electricity as they undergo friction with other materials. The lipid layer on the surface of regenerative substances, such as skin and hair cells, and even synthetic lipids, are responsible for positive static electricity. When mixed with a sudden electrical current of something such as electrocution or electrical shock, the growth of these cells can be affected so that they either mutate or stop reproducing altogether. Also, the way that electric shock affects a person's body depends on their health, the amount of electrical current, and the length of time of exposure, as well as environmental factors such as the presence of moisture. The danger also depends on where the electricity enters your body and where it exits. If the electricity enters your body through your left hand, it is going to exit into the ground through your left foot, passing directly through your heart along the way. This can cause an electrical injury. Some of the electrical injuries that there are include cardiac arrest due to the electrical effect on your heart, muscle, nerve, and tissue destruction from a current passing through the body, or burns from contact with electrical source. Jay Fiziol conducted an experiment where he demonstrated the possibility of a non-invasive modulation of motor cortex excitability by the application of weak direct current through the scalp. To do this, he placed a saline-soaked pair of surface sponge electrodes to a person's scalp. Then, the shock was delivered by a specially developed battery-driven stimulator with a maximum output of 1 mA. If you look to the right, a figure depicts how much electrical shock was applied based on the average age of a person. In the first trial, different electrode positions were tested to find the optimal positions for stimulation. In the remaining trials, the optimal electrode arrangement was used, which led to significant and reproducible excitability changes. In the different trials, the current flowed continuously for 4 seconds and for 1 to 5 minutes with an intensity of zero point 0.2 to 1 mA. Constant current flow was controlled by a voltmeter. Nearly all subjects were able to feel the current flow as an itching sensation. The current then exceeded an intensity of zero point 0.4 mA and or by perceiving light flashes as the current was turned on and off. Results show that the excitability changes of up to 40% revealed by transcranial magnetic stimulation were accomplished and lasted for several minutes after the end of the current stimulation. This excitation could be achieved selectively by anodal stimulation and by inhibition of cathodal stimulation. Also, by varying the current intensity and duration, the strength of the duration of the after effects could be controlled. From this, they were able to conclude that within a controlled environment, a small amount of electrical stimulation can cause excitement without any harmful defects to humans. In another experiment conducted by Agnew and McCreary, they decided to perform their main ideas on animals. Their experiments were performed from the perspective of animal studies, in which the stimulating electrodes were in direct contact with the brain. The data they collected indicated that the charge per phase used in most of the extracranial MEP protocols is sufficient to induce neural damage if the stimulation is applied continuously for several hours. However, in most cases, dispersion of the stimulus current in the extracranial tissue and skull is probably adequate to attenuate the stimulus charge density of the brain surface to a safe level, which is approximately less than 40 microcentimeters per centimeter squared. Agnew and McCreary were able to then conclude that the possibility exists that low resistance paths between the stimulating electrode and the brain may give rise to foci of high charge density. With this high charge density, the subsequent damage would be caused to the brain. An experiment was conducted by Dawson and some of his colleagues about electrical fields in the human body resulting from 60 Hz contact currents. Dawson's idea was to relate current density in electric field within excitable tissues and bone marrow due to contact current. However, with the voltage he had in mind, a shock to a person would excite their tissues so much that they would become damaged, or worse, death could occur. So instead, he decided to use a mannequin-like figure to represent a man. So then he created an anatomically correct adult model to use, as well as a proportionally downsized child model. Dawson was able to define 3 pathways of contact current that were modeled through his mannequins. One of them being hand to opposite hand in both feet, the second one hand to hand only, and the third one hand to both feet. Because of the adult model's larger size relative to the child, it showed to have a lower electric field and current density value and times per unit of contact current. After experimenting, Dawson was able to then conclude that for a contact current of 1 mA, which is the occupational reference level set by the International Commission of Non-Ionizing Protection, the current density in the brain does not exceed the basic restriction of 10 mA. However, he found that the restriction was exceeded slightly in the spine, and by a factor of more than 2 in the heart. For a contact current of 0.5 mA, which is for general public reference, the basic restriction of 2 was exceeded several fold in the spine and the port. In a final experiment completed by Kasuni, Hooney, and colleagues, they discussed their thoughts about finding imaging of current flow in the human head during transcranial electrical therapy. Being a newly developed topic and one that is rarely researched or experimented on, their findings are very exciting and intriguing. They use magnetic resonance electrical impedance tomography, or MREIT, techniques to encode current flow and phase images. And for human subjects, they use MREIT to measure magnetic flux density distributions caused by tach currents, and then calculated current density distributions from these data. Computational models of magnetic flux and current distribution were also constructed using contemporary collected TI weighted structural MRA images to compare predicted and experimental results. They were then able to find consistency between experimental and stimulated magnetic flux and current density distributions using transtemporal and anterior posterior electrode montages. Any differences that they found would indicate a need to improve models to better interpret experimental results. While human subject data agreed with computational model predictions in overall scale, differences would have resulted from factors such as effective electrode surface area and conductivities assumed in models. Cassina-Hooney was able to conclude that this method may be useful in improving reproducibility, assessing safety, and ultimately aiding understanding of mechanisms of action in electrical and magnetic neuromodulation modalities. This has been Electricity and How It Flows Through the Body. Thanks for watching.